Area of surface of revolution. We start with the surface area of some of the well-known geometric shapes. For example, the surface area of a rectangle is the length times the width. It is just simply the area. The area of the square is s times s or s squared. The area of a cylinder of radius r and the height h is 2 pi rh, not including the top or the bottom. This is because if we cut the cylinder and unfold it, we obtain a rectangle with the length being the circumference of the cylinder, which is 2 pi r, and the height is h. The area of this rectangle is 2 pi r times h, which is the lateral area of the cylinder. Next, we are interested in the lateral area of the cone, the area around the cone, of radius r. If we cut the cone from the vertex to any point on the rounded circular edge, then unfold it, we obtain a sector. This sector is a part of a larger circle, where the arc length is the circumference of the base of the cone. But the circumference of the base of the cone is 2 pi r, then the arc length of this sector is 2 pi r. If the slanted side of the cone is L, then the radius of this sector is L. It is part of a larger circle whose radius is L. The area of this sector is 1/2 the radius squared times theta in radian, but the radius is L and the angle is theta. But the length of the sector is 2 pi r. It is also computed by L times theta, the radius times the central angle. And so theta is 2 pi r over L. So we can rewrite the area of the sector as 1/2 L squared. We replace theta with 2 pi r over L, and we simplify this expression to end up with pi rl. R is the radius of the base of the cone, and L is the slant side of the cone. We're now interested in the area of the truncated cone, only the area around the truncated cone, not including the top or the bottom. If the radius of the larger circle is r2 and the radius of the smaller circle is r1, if the slant side of the truncated cone is little l, the side of the smaller cone is L1, and the side of the larger cone is capital L, then the area of the truncated cone is the difference between the area of the larger cone and the smaller cone. The area of the larger cone is pi r2L minus the area of the smaller cone is pi r1L1. But L is the sum of L1 and the little l, and so the area of the truncated cone is pi r2L1 plus pi r2L minus pi r1L1, or lowercase l. We then rearranging the terms to obtain pi r2L plus pi r2L1 minus pi r1L1, and then we factor out pi L1 times r2 minus r1. But to obtain a more useful expression, we observe that we can form two similar triangles in the diagram. The larger triangle comes from the larger cone, and the smaller triangle comes from the top smaller cone. Labeling these two triangles with the corresponding length, along with the fact that they are similar, we obtain r1 over r2 equals L1 over capital L. R1 times capital L equals R2 times L1, but capital L is L1 plus little l, and so R1 L1 plus R1 L equals R2 L1. Isolate R1 L to obtain R2L1 minus R1L1, and we factor out L1. L1 times R2 minus R1 equals R1L. And so the area of the truncated cone is now pi R2L plus pi L1. R2 minus R1 is now R1L. Factor out pi L. The inside factor is now R1 plus R2. If we take the average of R1 and R2, then the area of the truncated cone is now 2 pi RL, where R is the average of the two radii. This is the area of the truncated cone, not including the top or the bottom. Now suppose that we take the curve f of x and we rotate about the x-axis. We form a solid, and we're interested in the surface area of this solid. To estimate the surface area, we divide this into many sections. Each section is a truncated cone, whose surface area is 2 pi RL. This is the area that we derived earlier. The area of the truncated cone on the ith interval is 2 pi Ri Li, where the radius Ri is the height of the function f of xi, and Li is the arc length of the curve on the interval, where the difference or arc length ds is 1 plus f prime of x squared dx. This is the arc length formula. If the function is expressed in terms of y, then ds is the square root of 1 plus g prime of y squared dy, depending on whether the function is expressed in terms of x or in y. The total surface area on the interval a comma b is the sum of all of these surface areas of the truncated cones. There are n of these truncated cones. Each has the surface area of 2 pi times the radius f of xi times the arc length, which is ds. F of xi is the radius of the rotation, and ds is the arc length. This ds can be expressed in terms of x or y. This is the differential arc length. We move 2 pi to the front of this summation. The sum goes from I equals 1 to n, f of xi, where ds is the square root of 1 plus f prime of x squared dx. Note that in the beginning, when we estimate the arc length was the square root of 1 plus delta y over delta x squared times delta x. As n go to infinity or delta x go to 0, this is the definite integral from a to b, 2 pi f of x times the square root of 1 plus f prime of x squared dx. If the function is expressed in terms of x. If the function is given in terms of y, or it is more convenient to work with g of y, then the surface area is 2 pi, the integral from a to b times the radius in terms of y, times the square root of 1 plus g prime of y squared dy. The variable of integration is y, so all of the expressions inside the integrand have to be in terms of y as well.